Okay, welcome everybody. Hopefully everyone can see this. If not, let me know. Let's see. I'm just going to try to make this bigger. Okay. Well, welcome back, and let's. Sorry, I'm just. I have two computers, so I keep trying to use the wrong computer to move the video window, not realizing that I'm projecting it from the other computer. Okay, so what we're going to talk about today is computational models. So last week we talked about, why do people use FPGAs? How do they compare to processors and to ASICs at a high level? FPGAs are basically a blank sheet of paper. Well, they're not quite blank, but basically because you can rewire them at such a fundamental level, you can really organize your computation in a huge number of ways. We talked about a streaming method to organize a computation and a sequential processor-centric way to organize a computation last week. Today, and this will probably take us more than one lecture, but we're going to talk about computational models. So basically ways that you can think about your computation and organize it. So depending on what kind of computation you're doing, you can get higher or lower performance and higher or lower area based on how you organize it. So we're going to talk about some models to help you think about system architectures and computational models. The reading for this week is very relevant to that. So it's chapter 5 of the Reconfigurable Computing book, which covers the same topic. Doesn't use the same examples, not exactly the same terminology, but it's pretty related. So I think it's a very good complementary thing to read. And as usual, you submit a questionnaire before next class, so September 23rd at 4 p.m. And you need to submit at least 10 to have a chance at a full 10% on this component of your mark. Assignment 1, which is going to be implementing a couple of different compute models and comparing them to see how efficient they are. You'll go through 3 compute models, but one of them, the most basic one, will give you. You're going to implement a basic computation circuit to do a Taylor series expansion and see how fast and how efficient you can make it with different compute models and different optimizations that are related to what we're going to talk about this week and next week. So that'll be released soon. You'll be given about 3 weeks to work on it, and it has a significant embedded tutorial. I'm not assuming that you are familiar with the CAD tools that we're going to use, which are Quartus and ModelSim. So a part of this assignment is to get familiar with those CAD tools. It does assume that you know basic HDL design, and it's easier to do in Verilog because the test benches we're giving you are in Verilog. But we don't assume an extremely deep level of HDL knowledge. So if you're a bit behind on HDL, I'll post a couple of resources of where you could go get up to speed on that. It is possible to learn what you need as you go along if you aren't that familiar with HDLs. Any questions on that, any administrative items? Okay, so in that case, we'll go into the main topic of today's lecture. And let's see how well I can write this down. So what we're going to talk about today are compute models and system architectures. I guess I wrote up there already. And I told you the reference is chapter 5 of the Reconfigurable Computing book. So we could use a very general compute model. For example, communicating sequential processes, which is often called CSP. All right, has anybody heard of this? Is this ringing any bells? There's no particular reason you would have heard of this, but I'm curious if anyone has. So if you have, you can pipe up in the chat or unmute yourself and say, I've heard of it. And you can be a hero to all the people online. They'll be amazed that you've heard of it. You could even Google it right now, and then you could say, I've heard of it. No one will know that you secretly Googled it. So if not, fear not, I'm going to tell you what it is. Okay, so it's very general, and you can describe pretty much any computation that I can think of this way. So what is it? Maybe I'll tell you a couple things about it. This actually won the Turing Award, so computer science's highest prize when this compute model was proposed. It was proposed by the same person who developed Quicksort, so Tony Hoare. So he was a very productive computer scientist because he came up with one of the fastest sorting algorithms, and he also came up with this compute model. Actually, okay, so someone's asking, is it possible to zoom in? So I think it is. Let's see. How's that? Is that better? And thank you for that comment. I would much rather people say, I can't actually see or hear what you're doing than just kind of suffer in silence. Okay, so there's a Turing Award winner. It's by Tony Hoare. Okay, so what is it? It basically looks like pretty much any hardware you can think of. You basically define processes, which could be modules, they could be software programs, so something that does some computation, and it does that serially. So this is a process, and it's doing something. So it could do it serially. Well, it is doing it serially. So that could be software, it could be hardware. And it communicates, though, with other processes with signals. So it's sending events or signals to other processes. So this process is executing, and every once in a while it sends an event to this process, which might send some events back. Okay, so these are events. And this process also are communicating with events. And it turns out this process only sends events to this other one. So I've got 3 different sequential processes that are communicating with events. If you think about that, that looks a lot like the way Verilog works. It also looks like parallel programs, and a degenerate form of this, where you only have one big process, is a sequential program. So it's really powerful. This can describe pretty much anything. Let's see if I can get a finer tip here. Yeah, let's go to that. Okay, so it's very powerful. And Andrew, if this, as I'm writing, if you go at is worse, that's harder to read than the other one, let me know. Okay, so you're my
I think the bolder one is better.
All right, so I'm going back then. Okay, thank you. Okay, so it's very powerful, but it gives very little guidance. It's very generality, kind of means it can describe anything, so it's kind of beautiful from a theoretical point of view, but it doesn't let you reason much about systems because it could be anything. This can describe anything from a multiprocessor program to a single processor program to basically an arbitrary block of Verilog modules interacting in any way you want through a bunch of signals or events. Okay, so it doesn't help you in reasoning about implementing a design. Once again, if my writing's a bit messy, you can look at my notes on Quarkus so that you can see the non-messy version as well, or less messy version. So a good rule of thumb is don't use when you're thinking about how you're architecting a hardware system, this is a very general model, it's good to understand, but while you're organizing the computation, use the most restrictive model that you can, okay? And so we're going to start with very restrictive compute models that have a lot of conditions, but they help you understand how can that turn into efficient hardware. And then if you can't meet all those conditions, we'll say, well, how could we change the hardware to relax those conditions? And we wind up with a system that is somewhat less efficient, but more general. So that's kind of the topic of this lecture and probably much of next lecture as well. Okay, so my guidance to you is to use not the most general model you can, but the most restrictive model that we're going to talk about. And we're kind of talking about 2 things. The textbook talks about this as compute models and system architectures. They're kind of closely related. Depending on how you think about your computation proceeding, it kind of pushes you towards a certain hardware architecture. So the textbook makes a distinction between those 2 things. I'm not going to make a very fine distinction between them because they're pretty closely related. Okay. What we talked about last week was, let me clean that up a little, streaming data flow. So we already talked about we talked about 2 compute models. We talked about streaming data flow, and we talked about a simple sequential processor. So streaming data flow is what we talked about last week, and it's nice because it maps well to spatial hardware? Okay, but it turns out that there are a bunch of different variations on this streaming data flow theme. So first thing we're gonna do is we're gonna look at a bunch of variations on streaming data flow. Let me remind you of what that is. So it means we have a sequence of input values. Okay, so not one value, a stream in time. Okay, those go into a register. I'm gonna do some operations. So maybe I've got an operator F, I've got an operator G, and then I capture my output in another register. And so now I've got an input stream and I've got an output stream. And I might have more modules here. So the streaming computation could be a lot more complicated than I showed here. And we talked about one of the nice things about this is that we can pipeline it. So we could put pipeline registers in the middle of this computation and get higher throughput because we know there's a whole long sequence of data. All right, so I'm going to put letters on all the different compute models that we're talking about. So A is our first kind of most basic or very restrictive, but very hardware friendly compute model. Okay, and that's called, it's got a long name, single rate synchronous data flow. Whoops, let's see if I can write that better. Okay, so it's restrictive. How is it restrictive? So it's restrictive because first it has static operators. All right, so here's the first, what do I mean by static operators? So you don't know, I just made up that term, but can anybody guess? What do I mean by that? So check to see if anyone is out there. So if you got an idea, you can type it in the chat or unmute and just say, here's what I think static operator means. Looks like nobody's willing to take a shot. Okay, so the operator is prefixed. Operator R performs the same function. So yeah, that's exactly right. So thank you, Mike and Iggy. We do the same thing all the time on every item in the stream. And FPGAs are really good at that, right? We configure the hardware. We saw that it's actually not that easy to change the function of the hardware because we have this enormous configuration. So this is actually very friendly to FPGA hardware. So static operators. So we can do the same thing to every single data item. And synchronous data flows. So, and it's single rate. What that means is that data flows. What the single rate means is data flows through all the operators. All operators at the same rate. Okay, so this is very efficient in FPGAs. Okay, so flowing through all the operators at the same rate means we can have one clock, which is great. We do one thing, which means we configure, and the hardware does that over and over again. And we can pipeline it, because this is streaming, and we're constantly doing the same thing. It's actually a nice style to pipeline to increase our parallelism. Okay, so what that means is this F operator up here. So if I look inside that F operator, it's probably composed of some sub-operators, some smaller operations that could be smaller hardware. So let's say when I look inside that F operator, there's actually an F1, which goes to an F2, which goes to an F4. Okay, and let's make this graph of computation a little more interesting. So F1 also sends its output data to F3, and F3 needs data from F1 and F2, and then it sends it on to F4, which sends on the output. Okay, so we've kind of gone deeper inside of F to see what's in there. Okay, I see Camilo's got a good idea about how this could fit well into clock domain crossing, but we're not going to get there yet. So this is single rate means I can just use one clock everywhere. which is limiting. So there's some computations where that's actually going to be a problem. But if I can live with that limit, it's actually going to let me make extra efficient hardware. Okay, so I just drew this diagram of what's inside F to see, well, how could we increase our parallelism by using pipelining? Pipelining is probably your best optimization. Well, I mean, I shouldn't say best, but it's a great optimization in FPGAs. It is the best way to exploit parallelism in FPGAs. So, there are many ways you can go after parallelism. You can replicate functional units so that you have a bunch of functional units that are all working on different data items and so on. Pipelining is generally even better than replicating a bunch of functional units and having them all work on different parts of the problem in an FPGA. So it's the first thing you want to think of when you're trying to get higher performance out of an FPGA design. And it's basically because FPGAs build tons and tons of registers. So the cost of pipelining is very low. You usually have extra registers lying around anyway. And it keeps your data very local. Your data is distributed on all these wires. So again, we don't have a centralized state. And if we just start putting pipeline registers in there, we keep the data very distributed. So we avoid any bottlenecks where we might be gathering a bunch of data together and then broadcasting it out to a bunch of replicated functional units. So pipeline's a great optimization. Okay, so hopefully I convinced you you want a pipeline, especially in an FPGA. So they are very friendly to deep pipelining. Okay, so then the question is, where can I pipeline? Okay, so we're kind of looking at this single rate synchronous data flow and looking at, we like it, how can we optimize it? So we want a pipeline. That's our first technique and maybe our most powerful technique. All right, so looking at this, if I want to pipeline this computation, so this F computation that I'm showing you here, where should I put my pipeline registers? What's a reasonable place to pipeline this? What's a legal place to pipeline it? You can't just stick registers anywhere you want without breaking your computation. So there are some rules you have to follow. And then there can be choices that are better than others, even when multiple things satisfy those rules. So does anybody want to unmute yourself if you have the courage, or type in the chat otherwise? Where would you pipeline this? So you got to tell me where to put the registers. Okay, at the input output of the function. Okay, so like you're saying, put a register here. Is that right? And there. Is that right, Marius? Okay, so we could put them at the input and output of the function, which lets us overlap F with other blocks. So that's a good idea. Now we can go deeper. I told you that FPGA is very friendly to pipelining, so we can pipeline a lot. So I see some other ideas of pipeline between F1 and F3, okay? All right, so I'm gonna start drawing this down here. So let's draw, let's make this solid. Let's say that is, we're gonna do that. Okay, that sounds good. Now I wanna go inside this block and I wanna pipeline some more. So I saw ideas of, let's see, I see lots of ideas. This is actually interesting. Can I keep track of the whole chat? So let me expand my chat window here so I can see all the ideas at once.
I can help with that.
Okay, so I see between F1 and F3. Okay, so let me draw this again. All right, so we've got the input registers. I'm just gonna leave those out for now, but let's say that we have those, and now we're looking for more. Okay, so here are all my blocks. All right, I'm even gonna get fancy and I'm gonna try changing my color to red. Okay, so we had one suggestion of pipeline between F1 and F3. So could I put a pipeline register there? Is it okay to just put one pipeline register there? And that may not be what you mean, but let's just think about that. Is it okay to put it there? Yeah, so various people are saying no. So, and it needs to be balanced. So the rule for pipelining, you cannot tell that someone has pipelined let's see, the rule for pipelining is that you must add the same latency to all input to output paths, okay? Otherwise, your latencies become unbalanced at various functional units, and therefore you don't do the same computation. So if I put a register only here, this F3 is going to be doing a different computation. It's going to be computing a certain value from t equals 1, and its other input is coming from a clock cycle later, t equals 2. And so that's a problem, right? So I can't just put a register between F1 and F3. I have to make sure that I balance all the latencies of the paths through here. So whatever the latency is right now, which right now is essentially, you could call it 0 or 1, I got to make sure that their latencies can increase, but they all have to increase by the same amount. Okay, so I saw some ideas of how to do that though. So let's see. I see after each functional unit plus doubled on F1 to F3. So F1 to F3. Okay, so that actually sounds like it'll work, but I'm going to try a simple one. So let me draw a couple of them. I got lots of ideas here, and I don't think I can keep track of them all. So could I do this? Could I put a register here, put a register here, and put a register there? So what do you think? So I put 3 registers in here. Does that look like it's legal or not? So I'll let you think about it for a minute. And again, the key question is, from input to output, do all paths change in latency by the same amount? So I just added latency to my design. Did I add more latency to certain paths than other ones? Because if I did, it's broken. If I match them all, then it's delayed. Everything comes out, for example, 1 cycle later, but other than the fact that everything comes out 1 cycle later, I do the same computation. Yeah, so people are saying it's legal, and it is. If I look at this path, that's 1 extra cycle. If I look at this complicated path, that's 1 extra cycle. And if I look at this third path, that's 1 extra cycle. So all my paths, I added 1 cycle to. So +1 everywhere. So it's okay. All right. Let me do another test. So the fundamental rule of pipelining is balance all the latencies from input to output. This, what I've drawn here, is what's called a feed-forward circuit. So the data flows from inputs to outputs, and you can actually define a data flow direction. So that's actually a nice style of circuit. It's because it's easy to pipeline and therefore easy to get high performance on. For those feed-forward circuits, if you can define a cut between the inputs and outputs, and you put a pipeline register at every one of the edges that you cut, it's legal. And you can see I just did a cut. So this dashed line is a cut, but that disconnects my inputs, which in this case is only 1 input, from my output. So I put a pipeline register everywhere on that cut. It's fine. And basically the edges are always going the same direction across the cut, which is because this is a feed-forward circuit where we can define which side is input and which side is output. This is a shortcut. For this style of circuit, a cut will lead to balanced latency. So it's often an easier way to see how can I pipeline. So kind of an important special case. Let me draw another one. See if you think this one is legal. Okay, so this is F. Just draw the exact same diagram here, but I'm going to try to pipeline it differently. So F1, F2, F3, these both go to F4, goes my output. Okay, and I'm going to switch back to red, I'm going to put a pipeline register there, and I'm going to pipeline register there. Whoops, and I forgot one connection. So I forgot the connection there. What do you think? Is this a legal pipelining? So yes, I see a chorus of no's. Anybody want to say why? What did I do wrong here? Yeah, so I need it from F2 to F3. Yeah, let me think, is that actually going to work or not? So I put it between well, so this is definitely broken. I don't actually know if I can fix this one, but basically you're right. So you guys have correctly flagged. Let's see if I can get an even different color. Let's see here. So this path, I have actually added 2 cycles to. right? And this path I've added 1 cycle to, and this path I've added 1 cycle to. Okay, so I got a +1 here, +1 there, and a +2 there. So latency is not equal. Okay, so it's not okay. You can also see that it fails my cut test. This I didn't cut all the edges from input to output, so it doesn't disconnect my circuit. I could have done, so there are various other pipelines I could have done, right? There'd be a cut here would be legal, a cut here would be legal, and we already showed the cut that, that goes through the middle. So all of those cuts would be okay in this case. Okay, and someone's telling me how to, Enrique is telling me how to fix this, put one between F1 and F3, and another between F2 and F4, you can fix it. And I think that's right. Yeah, so you're right. If I put 2 more registers here, so let's switch to another color still. I can figure out the color one. Okay, this is, if I put 2 more, let's see if I can make this go away. If I put a register here and I put a register here, it would now be balanced, okay? And in fact, if I did that, you can see that what I've done is I've pipelined on 2 cuts. I pipelined on this cut, and then I've also pipelined on this cut, and that's fine, right? You can pipeline over and over again, increasing latency by 1, then by 2, or equivalently for this special case of a feed-forward design, you can put more and more cuts in and put pipeline registers on all the edges cut by each of the cuts. And your circuit tends to get faster and faster. And again, in an FPGA, because it's so register rich, in an ASIC, you might go, well, you know, should I really put all those registers in? There's an area cost to them, and maybe I've overdone it. In an FPGA, you have to pipeline a lot before it starts costing you area because it is so register rich. So you can tend to pipeline even more deeply than you do in other hardware structures. All right, okay, so we talked about legality. And let's see if I can change myself back to black here. Okay. What about quality of cuts? Let's see. So Andrew, you're asking why doesn't it work? Which one? Which one doesn't work?
So just to clarify, if we make a cut diagonally from the top left to the bottom right, why wouldn't it work?
From the top left to the bottom right. Okay, so I'd cut that edge, and I'd cut that edge, and I'd cut that edge, right? Let's see. So then I've added latency there, and latency there. Yeah, so it fails my most fundamental test if it didn't add the same. So I think you're asking, what if I did a cut here? Is that right?
Yep. Yep.
Okay, so I guess going back to the more fundamental test of did it balance my latency, it fails that. And that's the really fundamental test. Now, why does it, now it appears that it disconnects my inputs from my outputs. Is that right? So you're saying, well, why does that cut not work?
Yeah, so I was just clarifying that the cut test is not the only way of deciding it, right?
Yeah, the cut test is a shortcut. The real test is a latency one. And the cut test gets tricky in cases like that. Basically, the cut test, it's because you're, and this actually is exactly what, let's see, exactly what Camilo said. When you do the cut test, all the edges have to go from one side to the other. So the direction matters. So if I do the cut test on this top left to bottom right one, you'll see that, let's see, let me highlight this. We'll play with this highlighter. This edge is going, you know, from partition 1 to partition 2. Oops, it's hard to write with the highlighter. This edge is going from 2 to 1. So that basically just broke my feed forward. Like I'm not crossing in the same direction each time. This one goes from 1 to 2 again. Okay, so when you do the cut test, direction matters. Which side of the cut are you going from and to? Does that make sense?
Yeah, it does.
But if you get confused, and it's actually easy to, the most fundamental one is you got to balance all the latencies. The cut test only works in a subset of designs that are, as I said, feed forward, because there are some other rules that it doesn't capture. Okay, but feed forward designs are an important subclass. So and you're going to use them in assignment 1 and 2. You're going to largely be able to do things with feed-forward efficient circuits. Okay, so let's talk about what we want in the cuts. So we needed a legality in pipelining, so we have to balance all the pipeline, well, all the latencies of the paths. We have to add the same amount to all of them, which we can turn, as I said, for this important subclass of feed-forward circuits into a cut test. We have to pay attention to the direction we're crossing the cut in. What do we want in the cuts? So I showed you here we could make lots of different cuts even in a little circuit. What do we want? If I'm choosing between a few different cuts, which ones are going to be sort of more desirable than others? And I can let you keep looking at this one. So more stages. So what do you mean by more stages? I think maybe you both are saying the same thing. So more stages, or try to cut the longest computational path continuously, balance latency of cut path. Yeah, so one of the things we want to do is pipelining helps us by getting a higher clock frequency. So that's how we're getting parallelism. We're having multiple things in flight in different pipeline stages, and that allows us to clock at a higher speed, but still have one piece of data come out every single clock cycle. So the first thing you want to do when you're pipelining is try to have equal delay or equal logic on both sides. Really, you want equal delay, and a proxy for that is logic. You know, often you don't quite know what the delay is on one side or the other, but you may know how much logic you're doing on both sides. Yeah, so that's your first goal. Try to cut the critical path in half, and then you can clock approximately twice as fast. And you can keep doing that, right? So you can do it multiple times and keep going faster and faster. The other thing that there's another thing that you can balance for area. So I told you registers are plentiful in FPGAs, but they're still not infinite. So you can sometimes wind up with multiple places to cut that will cut your critical path, you know, reasonably evenly. But basically, if some of those cuts have fewer edges, so if you have fewer edges, you basically save register count. Okay, so the fewer edges you have to cut, the fewer edges you cut, the fewer registers you add. In an ASIC, that directly translates to area. In an FPGA, it's less direct because the registers have been pre-built, but it does help you avoid running out of registers, and it does save some power. Registers take power. Does that make sense? Okay, so let's talk about another thing. So this was a feed-forward design that I was showing you as an example. Let me show you another simple example of a little hardware block. Okay, so I got a streaming piece of hardware. So there's a sequence of X's coming in. I'm going to call X of I. Yeah, and so Peke is saying, what about the amount of cut, which is basically the number of edges. You know, fewer edges or registers cut. So the fewer edges you cut, the fewer registers you have to put in. So those are also highly desirable cuts. Okay, so let's look at another simple streaming circuit. So I've got a sequence of X's coming in, and it's going to go into, I like using F for operators, so it goes into a function F1, goes into a function F2, gets registered, it's going to go out, and the output we're going to say is Y of I, okay? But we're going to have a little bit more complexity now. This is actually not feed forward. The output actually affects, previous outputs actually affect future outputs. So this could be, for example, an infinite impulse response filter. There could be lots of other things too. It could be a finite state machine and so on. But there are types of filters that take into account not just the inputs, but also prior outputs. And obviously finite state machines take into account what your current state is. So they pay attention to their outputs too. So if I write down, well, can I pipeline this? So my critical path here is, let me change the color. Okay, so my critical path is basically going to be around this loop. I need to go from the output of this register all the way through all this logic, so 2 blocks of logic and back to its input. So the delay of that is going to limit my circuit speed. So I'd like to get rid of that, and I can see there's a nice place where I could cut this critical path, okay? So if I put a register here, that's going to cut that critical path roughly in half, and I'm going to be able to clock this thing roughly twice as quickly. So that's going to increase my throughput. So can I do this? So if you've been lurking on the chat saying, I wish I'd put something in, but I was too nervous, you got a 50-50 shot. On these yes/no questions, you just want to go for it. It's like, that's where you want to go. I'm going to show participation. Let's see. So I see various people saying, yeah, that they can pipeline this. Okay, so lots of people saying, sure, go ahead and pipeline it. And I saw one longer answer. You can pipeline it if the historical requirement doesn't include the last data point. Let's see, you also have to register to the feedback path. Okay, so lots of yeses. One comment of maybe I need to add a register here too. So add a register to the feedback path. Okay, so let's think about that, but let's not do that yet. Let's write down what the function this is doing. So let me turn this back into black. Okay, so right now, the function that we're computing is y of I is equal to f2 of something, okay? So f2 of f1, right? So I just said f2 of f1. And what are the inputs to f1? The inputs to f1 are x of I and the previous y value, okay? Y of I minus 1. Okay, so I'm kind of writing out, I'm not just writing out entire streams now. I'm basically saying, you know, what actual private value am I working with? Okay, so that's what my original computation was. I think Mike is getting nervous now. He's saying he doesn't think we can add a register to the feedback path. So there's now debate over, should we add it to the feedback path up here or not? Let's first just look at this one register. Okay, so we've added one register between F1 and F2. Let's look at, let's call that Y prime. Okay, so Y prime, you know, with pipeline. So Y prime of I is equal to, okay, so it's still some function F2, okay, of a function F1. And what are the inputs to F1? Okay, so it's still X of I, so none of that has changed. But it's no longer Y of I, it's actually Y from 2 cycles ago. It took me 2 cycles from X of I getting here, so a certain value, maybe 6 getting there. It takes 2 cycles for that to produce a Y. Okay, so we're actually computing on Y of I minus 2. And Camilo's saying, yeah, Camilo's saying this can't be pipelined because we can't start the computer the next data point until we have the previous one fully done. And that's right. Basically, we have a dependency here. We want to compute the next Y as a function of the current X and the previous Y. And if we don't know what the previous Y is, then we just cannot start the next computation. We don't actually know what our inputs to this block are. Whoops, that was not what I intended to do. We don't know what our inputs to this block are because we haven't computed the proper Y yet. When we put this register in there, what we did is we just started the computation early anyway, but we've changed the computation. It's now a function of X of I and Y of I minus 2, which is just different. So if this was a finite state machine, it's now broken. It just does not compute the same thing that it used to compute. If it was an infinite impulse response filter, it doesn't filter properly anymore. It does something different than we intended. So we can't do this. There was a suggestion of what if we pipeline the feedback path? That doesn't fix it either, okay? If we pipeline the feedback path, we're now basically computing a function of, that would make us compute a function of X of I and Y of I minus 3. Okay, so it in some ways makes it even worse. So we can't fix it. Let's see, so Enrique is saying you can add a register pipeline between every register result. So you can add a register after Fi because it's already calculated. You can pipeline the feedback. You also pipeline the Xi. There is actually no way to pipeline this, basically. So you cannot change the latency of a loop. So that's your second constraint. for, so that's your second constraint for pipelining. So you can't change the latency of a loop. Which basically means you can't pipeline it. So these are dependencies. They're data dependencies, and you can't fix them. So Camila has an interesting idea, which we're going to come back to later. So Camila's saying, well, if that's really hurting our clocking, we could add stall cycles in the input. So in other words, we're only going to send an input every second cycle. And that's true. If you only sent an input every second cycle, this actually would start working again. Because essentially, it takes you 2 cycles to get the Y value that you need to go back, but you're just going to wait then. You're only going to send a new X value in every second cycle and things will work out again. And we'll talk about, there are cases where that can be useful. But what we'd really love to do is just pipeline this loop and make it run really fast, and we just can't do it, okay? So loops are important to try to minimize in your code. That's one of the reasons people like feed-forward designs that don't have any loops. It's actually one of the reasons for filtering. There are 2 basic kinds of filter. There's a finite impulse response filter where you only do, your outputs only depend on your inputs, and there's something called an infinite input response filter where your outputs depend on both previous outputs and inputs. And generally people prefer in hardware finite impulse response filters because they're easier to pipeline because they don't have these dependencies. So people try to get rid of their loops when they can, making it easier to pipeline and get higher frequencies. You cannot get rid of finite state machines from your entire design, right? Like, so you're going to wind up with some loops generally in your control. And let's see, so there's a question, should x of I be x of I minus 1 for pipeline equation? Possibly, it kind of depends on what I define I to be. So it's possible that would be more clear. And I actually always confuse myself when I do too much of this too. But you're right, in the pipeline equation, it's possible that I should have called that x of I minus 1 because I might not be using I consistently. I guess the key thing to focus on is the fact that addition of the pipeline register changes the computation, and you're just not allowed to do that. Okay, so does that make sense? Because that was a bunch of discussion about a very important optimization, pipelining. And again, it's because it's the most hardware-friendly form of parallelism. You just add registers, you don't add anything else, and you have multiple pipe stages working on different parts of the computation. The state's distributed. So you generally in hardware designs try to fully exploit as much pipelining as you can before you start looking for other forms of parallelism like replicating functional units. Okay, so that was our first form of compute model. So it was single rate, synchronous data flow. So now we're going to basically look at how can we make that a little more flexible. That compute model is very efficient. So if that does everything you need, it's great. It's really fast if you need to get high throughput. Okay, so let's move on to synchronous data flow though. So what do I mean by that? So the single rate meant that everything was on the same clock period, and all the data was flowing together in lockstep. Every single clock cycle, we got new data at every single functional unit. We can't always do that. So what if, let me give you some examples. So what if some operators produce more output than input? Okay, and I can give you some examples of that. Can't really think of an example where an operator produces more output than input. So the simple examples I gave you last week, like doing quadratic equations, it's not true, right? You send one number in, you get one number out. So it matches. But not all computations are like that. Can you think of a computation where the amount of output coming out is different than the input? And fear not, I have an example ready. Yeah, so Rakshith says binary to one hot. So that's a good example, right? So you go from a binary encoding to a one hot encoding, your output's going to be bigger than your input. And there are many examples like this. So if I go to filtering again, because that's a very important application of FPGAs. You can have something called an interpolation filter. So commonly used in various signal processing and communications application. An interpolation filter, basically, data comes in at a certain rate and you fill in the gaps. So maybe data comes in at 100 megasamples per second and you interpolate to take that up to 200 megasamples per second where you filled in, intermediate values. And that turns out to be useful for some of the downstream signal processing. Another example Camilo's given is packet parsing. So if you bring in one packet and it's being broadcast, then yeah, your function might output multiple packets or broadcast the packet based on what its header says to multiple places. So its output size could be bigger. So there are many examples where it could be bigger. You can also have examples where it's smaller, okay? And a simple one, as I just talked about, filtering is important in FPGAs and in communication systems. Interpolation filters, well, the opposite of an interpolation filter is a decimation filter. And also common in hardware signal processing systems. So what this means is maybe I have 200 megasamples per second that came in off an antenna. I do some early processing on that, and then at a certain point, I don't need to process every single symbol. So I can drop every second one or every third one. Say I drop every second one. Now I go from 200 megasamples per second down to 100. And I probably wouldn't do that at the very start. I do that after some processing, but I may decide that now my symbols have been processed enough that I don't need to keep them all. There's some redundancy. I'm going to drop every second one. Okay, so what does this mean though? So there's lots of examples where our output rate and our input rate don't match. So it means we can't run everything at the same rate. The hardware I was showing you before, every clock cycle, everybody had new data, but we're not going to have that in these systems that are generating different amounts. Okay, so what are we going to do? How are we going to tell when we actually have data to process when some modules are producing more data than others? So any ideas? I mean, you could try to make a finite state machine, but maybe there are other ways to do this. Don't worry if you have no ideas. Again, I have notes, so I'll move on to an idea. So a good way to do this. So yeah, Camilo's got you're 1 to 2 steps ahead. Clock domain crossing, back pressure, handshaking, use a Fifo. These are all good ideas, actually. Okay, so yeah, and you're actually kind of jumping ahead to the next model. So you guys are already going on to more advanced ones, but these are all good ideas. So let's do the very simplest thing that we can, which is not going to work all the time. So sometimes we're going to need exactly what people are suggesting, which is back pressure, Fifo, handshaking. But the first thing we're going to do is we're going to use data valid. Okay, so data valid to tag and synchronize our data. Okay, so what do I mean by that? So I've got, say, a function f1, it produces some data. I've got a function f2, it produces some data. That goes to another function g, and it produces some output. Okay, and it turns out that sometimes basically not every clock cycle do we have valid data. Okay, that's what this new compute model is saying. The amount of data that comes out is variable. So you could try to keep track of that with finite state machines and so on, but it's going to be a big mess. And it's going to be really fragile. So a better solution is you tag your data. You already had your data flowing through here. Maybe it was 128 bits of data. Maybe it was 12 bits. Maybe it was 256 bits, but it's probably multi-bit. And you tag it with a single bit valid, which is not too expensive, because if this is multi-bits of data, adding one more signal called valid is not that bad. And you do that everywhere. So all of these modules basically output not just their data, but this new 1-bit signal saying whether or not their data is valid. And we basically make sure that G only computes a new data item when both of its inputs are valid. So it naturally waits until it gets 2 inputs. So if there's imbalances in the amount of data that's created by F1 and F2, this kind of lines it all up again. So that's great. It also is really nice for pipelining. So remember, this is what I've shown here is a feed-forward design still. So if I draw my cut across here, I can pipeline this again. So I could pipeline this by putting registers in, it'll run faster. And I just pipeline both the data and the valid. So you don't even worry about the fact that some of these bits are data bits, is what you care about, and some are just valid bits, saying whether you actually have proper data that cycle or not. You just put the cut in, you pipeline them all, they all stay lined up. G only computes when it has both inputs valid, and then it produces an output where it says the output is valid. And everybody's happy. Okay, so this is a form of feed-forward control. So we've got a feed-forward design here, and we put a feed-forward control on it. Okay, so G is executing only when both inputs valid. And this model is still somewhat limited because G can't say stop. Okay, so G has to be able to, whenever it's got 2 valid inputs, it's got to produce an output because it has no method to tell F1 and F2 to stop sending its data. So G has to be able to keep up with however much data F1 and F2 send. So for us to use this model, we need to choose the speeds of F1, F2, and G so that no valid data is dropped. Okay, so G has to be able to keep up with F1 and F2, but it has no way to stop the data flow from coming. It can only tell when there is nothing for it to do. Does this make sense? So it's a very small change, right? It's very cheap because all I did was add a valid bit. So that could be, that could be a high overhead if my data was 1 bit wide, but usually my data is considerably wider than that. So Camille is asking in this model, what if F1 has valid data, but F2 does not? So in that case, G doesn't compute. Okay, so G will wait until it has valid data from both. And you're probably thinking ahead of, well, then what if F1 computes another piece of data? So yeah, there's also a risk here of if F2 doesn't have valid data and F1 keeps computing, maybe it overwrites the data that was meant for G before G processes it. So I think that's probably where you're headed, and you're right, there's a fragility in this. G has to be able to keep up with F1 and F2, and F1, you could get into cases even in that situation where F1 basically throws away data that hasn't been processed yet. So this is still a bit fragile, okay? And Maddie's saying, yeah, if we had a 1-bit accept signal and a buffer between them, that would help. And that's exactly right. So we're now going to move on to something that's a little more expensive. So adding those valids costs us a bit, costs us a little bit of control logic in G, costs us an extra bit on our data, but not too much. But we still have a fragility in a lot of cases where it, as Camilo and Maddie have pointed out, we could lose data. So let's go on to our next compute model. It's another form of streaming. Okay, so, and this is called dynamic streaming data flow. Whoops. The names of these don't matter that much. I mean, these are all data flow and streaming, that matters. The names are really just tags. You really just want to understand the concepts. Because I have trouble remembering like what are all the different detailed names of these two. Okay, so this basically overcomes some of the issues that Camilo and Madi just flagged. Okay, so what if the time to produce an output varies? Whoops, sorry for the messy writing. Lots of examples where this could happen. Let me give you one from math, and lots of math gets implemented in hardware. So remember back to calculus, if you're trying to figure out the zeros of a function, one of the techniques that's very efficient is called Newton-Raphson iteration. So you basically have the function, you have its derivative, and you guess how far you have to move in the x domain before the function will be 0. You're not exactly right. So once you go to that spot, you evaluate the function and its derivative again, and you refine your guess. And you keep repeating until the error is very small, until basically the function evaluates to nearly 0. The number of iterations you need to do to find what value of x drives this function to 0 is variable, right? So in some functions, it converges very fast because turns out that your guess based on the derivative and the current function value is very accurate, and in some it converges more slowly. So if you have that in your algorithm, and you might have this in a physics-based solver, then you can't say exactly how many clock cycles it's going to take to produce your output, which is basically, the x value such that f of x is equal to 0. You don't know how long it's going to take. All right, so fundamentally there's a variation. Other things, what if the amount of data varies? So there's a suggestion on our prior model of what about packet processing, where you might have some multicast, a packet that goes to multiple destinations. So that's an example where the output data could vary. There are lots of other ones. So what if the amount of data varies? Okay, so another example of that is Huffman encoding. Okay, so Huffman encoding, takes unusual bit patterns for your data stream and encodes them as long code words, and it takes common data patterns and encodes them as short code words. And by doing that, it compresses things. So it cuts your file sizes or cuts your bandwidth in a communication system, so it's good. But it fundamentally is using different number of bits its output bits vary depending on what you sent it. That is how Huffman encoding works. Short symbol patterns for common symbols and long symbol patterns for uncommon signals. So it's fundamental that it's going to vary. You could say, well, maybe our worst case, this is the most data or this is the longest it could ever take. You might be able to do that, but it's going to be inefficient. So you'd really rather not. So, and in some cases, you just may not be able to come up with any reasonable bounds. Okay, so we don't want to, or sometimes we just can't. Worst case, the time or data size. Okay, so the solution to this is actually one that several of you have already been, pointing out and jumping ahead to. So what we need to do in this case is, first, we might produce a burst of traffic, which this earlier architecture really couldn't handle. So the first thing we want to do is maybe I'll number these, that might be a little more clear. Okay, so the first thing we want to do is we're going to convert some pipeline registers to Fifos. Okay, so first input, first output buffers. Okay, so that's going to decouple our operators. We can have bursts of data, and the Fifos are going to capture them. They're not going to lose it. So there's a point before of, we could overwrite while G was busy. Maybe F1 overwrites data because F2 is not ready. So that would be bad. A Fifo can help us with that because we can store multiple data items. But in general, we also can't bound how unbalanced our computation would be. So it's usually not clear how big these Fifos should be in the worst case. Maybe in certain cases that I've given of Huffman encoding or Newton-Raphson iteration, it might take quite a while for the downstream logic to produce its output. And that might happen many cycles in a row. So we might need extremely big buffers. And in general, we might find the buffers are unbounded. Like in the worst case, we just can't say how big to make them because the downstream logic keeps taking longer than the upstream logic. So the FIFO, no matter how big we make it, there's some chance that it just overflows and we lose data. So if we can't bound the computation imbalance, which is pretty common that we can't bound it, the solution was already suggested by a couple of people, which is basically back pressure signals or handshaking. These are kind of synonyms, okay? So add back pressure signals, or several people suggested handshaking, which is the same basic thing with different names. Okay, so back pressure signal says, you know, am I ready or not? So a downstream module like G can actually tell F1 and F2 stop. I can't process any more data. You need to stop sending me data because otherwise we're gonna lose data. Okay, we need to assert these in time to avoid buffer overflow. Okay, so let me draw what that means. So let's take our little simple example of F1 and F2 feeding G. So we got F1, we got F2. Okay, so F1's not going to feed into a register anymore, and it's not going to directly feed G. It's going to feed into a FIFO. Same thing. Sorry, F1's going to do that. So is F2. Outputs of those FIFOs are going to feed G, and G is going to feed a FIFO as well. And that's going to produce our output. So this, you know, this has helped us, as I said. Like now we can tolerate G not being ready to compute for a while, but it's not going to work forever. So we need to put back pressure signals in. So from the FIFO, we basically add logic that says you need to stop. Okay. So that back pressure signal goes back to the module that's hooked up to the FIFO. And tells it to stop. And we're going to do that on all our FIFOs. So all our FIFOs can tell the upstream module to stop. And now this is a more general compute model. So it can handle if there are stalls in F1 and F2. It can handle if maybe F1 produces more data than F2 or G has to wait for a while. It's a distributed control scheme. Basically, the various, or sometimes called data flow control. The various operators are negotiating, am I ready or not? Let's see, and there's a question of with back pressure, can deadlock start being a problem for some circuits? So that's a really good question. It could be a problem in some circuits. And so yes, you could create a system where you deadlock. There's a classic paper by Carloni on latency and sensitive design. Because another word, this style of design is actually also sometimes called latency and sensitive design, or it's getting towards it. Latency and sensitive design is if you follow rules where you put FIFOs in these places, you tag your data with valid bits so you can tell when you actually have valid data, and you have these stall signals. So these back pressure signals could also be called stall signals, and it means that these modules have to be able to stall. Okay, so G, F1, and F2, they have to have a clock enable or some other method by which they will actually stop working. If you follow those rules, Carloni in this classic paper showed that if your design works without any of these FIFOs, then it will, well, basically if it works without adding in essentially generalized pipelining, which is something called an elastic buffer, basically like a FIFO, then it won't deadlock once you add them in. Okay, so that was a long meandering answer. I guess the shorter answer is yes. If you just added FIFOs and back pressure and you didn't think about it, you could add deadlock to a circuit. There are some classic papers that show if your original circuit, before you added in extra pipelining, didn't deadlock, then if you add in your extra FIFOs and pipelines following a certain set of rules, that you will not deadlock after that. It still means that your original system had to not deadlock. And you have to follow these certain prescribed rules. Hopefully that partially answers your question, but the short answer is yes, you have to think about, is deadlock possible? For a system like this, which is feed forward, you won't get deadlock as long as your FIFOs are big enough. If you have to be careful if you made very small FIFOs, you need to think carefully about whether, and you have loops in your design, you have to think carefully about, could you ever get a situation where you're waiting for somebody to compute a value, but they will never get that value because some FIFO is full, and you'll never pull anything out of that FIFO until the downstream module can compute. So with loops, you got to be careful that your FIFOs are big enough, because otherwise you could wind up in a situation where to take something out of a FIFO, you're waiting on some other data to be ready, maybe this path, and it will never be ready because it's waiting for some downstream logic. So you got to be careful with loops on how big your FIFOs are. Does that make sense? It's kind of a long answer. The short answer is yeah. With loops, you have to be careful. Yeah, and there's a question of what are these? Why is the FIFO going back? So this is basically my data path through the FIFOs. This is my data, my valid. This back pressure signal is like a single 1-bit control signal. So it's not the data that's in the FIFO. It's a signal that says you have to stop because the FIFO is going to overflow. Okay, when should this back pressure signal be asserted? So when the FIFO is completely full, like what is the logic that I should employ to compute this back pressure signal? Any ideas? Can I wait till the FIFO is full and then basically assert the back pressure signal? Okay, so yeah, Rakshi says yes. Another answer is when there's one thing less. Camilo said, yeah, so various people are saying, well, maybe there's data in flight. And yeah, I see we should do it early. So yes, we need to do this actually early. And actually see a couple of people who are onto the exact equation, which is basically, this is not full, it's going to be nearly full. Okay, and what does nearly full mean? It basically means if there's n data items in flight that we can't stop. So let's say G, when we tell it to stop, if it stops in one cycle, then the almost full signal can be generated when there's only one entry left in the FIFO. If G takes more than one cycle to stop, then we need to tell it to stop. Let's say it takes 3 cycles for G to stop. Then we're going to need to tell it when there are still 3 data items left in the FIFO. So, because in the worst case, we might get 3 more data items. So it depends on the latency to stop G. And so that latency might be 1 cycle, in which case we only need 1 item left in the FIFO when we assert nearly full. But inside G, we actually have a lot of control. We know our computation, we know all our inputs have arrived, and so on. So inside G, we might use a less flexible model. So inside G, we might still use pipeline registers, that we can't stall. So if G was pipelined, so it had 3 cycles of latency, then we should actually assert almost full when there are still 3 items left in the FIFO, because in the worst case, we'll get 3 more pieces of data. So this structure of FIFO plus back pressure is often called an elastic buffer, okay? And a pipeline register is sometimes called an inelastic buffer. So there are different ways of storing your data. This is FIFO is a more flexible way because you can stop it. It can store multiple data items. A pipeline register is much less flexible, but it's also more efficient. To build this FIFO, there are a couple different ways to build it. You could build it as a chain of registers with enables. That gets actually pretty inefficient pretty quickly if you have big FIFOs. So usually it's built as a RAM with read and write pointers. So basically little counters that are your read and write address. And for larger FIFOs, that's more efficient than building it out of shift registers. But it's significantly bigger and more power hungry than just building a single bank of registers to make a pipelining. Okay, so you often mix them. So inside modules like G, where I have a lot of control, I know once the data arrives, I'm just going to compute things. I'd probably use very simple pipeline registers. And then in between bigger modules, where I have less certainty about when my data arrives, how long it's going to take, etc., I can use these FIFOs and data valid and back pressure to negotiate. What do I do? Let's see. His question is, how would you choose the size for the FIFO? So that's a good question. Basically, one size is you do not want to, okay, so let me write that down. So size FIFO. So there are a few considerations. So generally you want to make it as small as you can to save area. In an FPGA, this is normally built out of a RAM plus a read and a write pointer, which are registers. That means in an FPGA, we're going to see later in the course that all the RAM's prefabricated. So you actually have certain discrete sizes of FIFOs that are equally good. So in an FPGA, sometimes you size the FIFOs pretty generously because once you're using a certain kind of RAM, you may as well use all of that kind of RAM because you're using the whole block anyway. The number one thing you want is you don't want to have stalls when your pipeline is fully working. Okay, what that means is if new data is arriving every cycle at F1 and F2, you want to, in the steady state, be able to process a new item every single cycle. That means that if it takes you, let's say it takes F1 3 cycles to stop, you want to make sure your FIFO has at least 4 items in it. Because if G is absorbing the data, you don't want to exert back pressure and stop F1 and F2 from working. And if F1 and F2 need 3 cycles to stop, and you only had 2 entries in your FIFO, you're going to be stopping them all the time, even if there's no real reason to do that, even if G is taking the data out as fast as possible. So one of the fundamental things is cover the latency to stop the upstream module. If you don't do that, you're basically going to insert all sorts of bubbles in your pipeline. Like you're going to be stopping the upstream module when you didn't really need to. So that's kind of the fundamental constraint. And then I guess beyond that, make as small as you can after that to save area. Except if you have to use prefabricated block RAMs on FPGA that have spare space. Okay, so when you know that you're using something that has spare space, then you can kind of be generous instead of carefully analyzing what's the minimum that's going to avoid putting bubbles in my pipeline when everything's going well and I shouldn't have any back pressure. You can just say, I know I get empty rooms, so it's going to make the FIFO bigger. And these back pressure signals, if these modules are big, can actually get slow. But just like anything else, well, you can actually pipeline these back pressure signals. If you pipeline the back pressure signal, you need to make sure that you change the logic that asserts the back pressure signal to assert it 1 cycle early. So you could go, well, that's a loop. I'm not supposed to be able to pipeline that. You can't pipeline it without changing your logic. In this case, you know what the logic does. I can put a pipeline register there as long as I change my logic for what is almost full mean. And I make sure I assert almost full one cycle earlier. So instead of checking for three entries left in the FIFO, for example, I check for 4 entries left. Let's see. And I think that's all I had to say about that style. I think, are there any more questions? If not, we'll take like a break for maybe 6 minutes, because I think I'm going slightly slower than I do on a chalkboard. Okay, so it looks like no more questions. So how about we take a break till 5:30, and then we'll reconvene. Andrew, I have a quick question. Can you hear the fan now or not?
No, I can't.
Okay, yeah, I'm using an external mic. The fan is kicked in, but I guess it's not as bad.
Yeah, it's much better than last week.
Yeah, I see Udib's asking, why would you pipeline the back pressure? You'd pipeline the back pressure if it's limiting your clock frequency. So you wouldn't do it unless it was causing you problems in clock frequency, but that can happen, right? So you have a back pressure signal. It may be going to a relatively large module, like if those F1s and F2s are relatively large, and it has to go through that whole F1 and F2 and basically tell the whole module stop computing. So that's often done as a clock enable on all the registers inside of, let me say F. So say F1's pretty big, right? So maybe it's inside of it, there are 5,000 registers and lots of lookup tables and multipliers and so on. The back pressure signal arrives. We need to stop F1, so it can't produce any more output. It can't corrupt its internal state. Okay, so it's also not okay for it to kind of start doing half computations. Like when it starts again, it's got to produce the right value. So the normal way you stop it is you put a clock enable on all of its registers. So if this back pressure comes back to F1 and it fans out to 5,000 registers as their clock enable, that means that signal's got a significant distance to travel, which means it's going to take some time. So that might limit the speed of your design. If I put a pipeline register on back pressure, I now have 2 clock cycles instead of 1 to distribute that back pressure signal to those 5,000 registers. And so that can help me, just what's half the wiring on one side of the clock of the register and half the wiring on the other side, and maintain my clock frequency. And again, to do that, the reason I can do that in this case is I know how to change the logic, right? I can basically say, well, assert the back pressure signal 1 cycle early because I know that I've got a pipeline register on it. And as long as I have a big enough FIFO, instead of checking, is there 1 entry or 2 entries? Let's say, are there 2 entries left? I'll just check if there are 3 entries left. So I can change the control logic and it'll all work. So by redesigning the control logic, you can pipeline loops. You just can't pipeline loops without redesigning something. Whereas these feed-forward designs, you can essentially pipeline them structurally. You can just take all these signals that cross a cut line and you can just pipeline them all, and you don't even understand what the circuit does, right? You can just mechanically pipeline it. You can't do that with loops. For a loop, you got to say this, if I were to pipeline it, it's broken, so I need to understand what this control logic or loop logic does, and I need to change it. Okay, so I'm going to try typing a few things because I'm a bit faster at that. Okay, so with streaming data flow with allocation, what does that mean? So it's another streaming data flow organization, but the idea is we can change. It's a little more general still. So we basically now move to a streaming data flow where we can deal with stalls, we can deal with different amounts of data coming out of different units, etc. And it all works. We use valid bits, we use backpressure bits, we use Fifos wherever we're not sure if all our data is going to be ready. And then, as I said, inside of these operators, if we're sure once the data arrives that we got everything we need, then we could use the more efficient, simpler streaming models where we just use regular pipeline registers. Okay, so streaming data flow with allocation. So what this one is you can change the operators or connections over time. And let me know if this is hard to read. I can switch back to handwriting, but I can probably type a little faster. Okay, so we don't need to do this if our computation never changes. So that's why filtering is great for FPGAs. Usually the computation doesn't change and you can just use one of the earlier models I talked about. But let's say our computation is changing sometimes. So we need to have some flexibility in what the operators are. So first method. Okay, so how can we, I'm going to tell you what let's see if I can figure out how to put dashes in the right spot here. Okay, so method one. It's kind of the easy way to handle this. So build extra flexibility in the operators. And so that's how we can deal with operators that change. So maybe sometimes we add, sometimes we subtract. Well, we can build an add or subtractor unit and have a control signal that decides every cycle whether we add or subtract. So we built a more complicated operator. Maybe we also have some differences of how our operators are connected. They're not always going to do this, have the same connections through all eternity. So if we have that, we need to build muxing into our interconnect. So instead of having just simple wires that connect one operator to another, we need to build something a little more complicated where we have switching, multiplexers. Okay, so let me draw an example of that. So that's a bit messy. Okay, so my favorite example of F1, but now I've got a couple options for F1. I've got F1 and I've got F1 prime. And sometimes I want to do F1, sometimes I want to do F1 prime. So in hardware, I'll build both. And then I'll build a multiplexer that lets me choose which one to do. Maybe I also want to do function F2. And both of these things feed a function G, which now we say that function G is a more general function than what we had before. So we'll call it gget. Okay, so let's say my G function that I had before. So let's remember what I had before. I just had F1 and F2 feeding G. So let's say my G function was just a certain mathematical operation. Let's say it was a certain quadratic function of my input X. So let's say it was that. Okay, and Ggen might be that I don't know the constants anymore. Instead of it being 181 times x squared, it's now a times x plus b times, or a times x squared plus b times x plus c. And these are, actually, let's make this a constant too. So let's say this was 10. Okay, so these three constants, b, a, and c, vary at runtime. So they might change every cycle, they might change every once in a while, whereas here, they never change. Okay, so maybe in my HDL, I define constants, but basically these are compiled into my design. And that helps in FPGA, so we can have extra compile time optimizations. The FPGA CAD tools are pretty clever. So if you tell them that these things are constant, they will build hardware that is more efficient because it only computes this exact function. If you want hardware where you can change A, B, and C, those have to be put in registers, and you have to build, normal multipliers, normal multiplication units. But if I know exactly what the values are, I can actually build special multipliers that are more efficient. Okay, so you can see that generalizing my operators is relatively expensive in FPGAs. So this G-gen, I lost some compile time optimization because I had to build registers to store these constants. I had to build general multipliers instead of specialized multipliers, so it cost me some. And let's see, make this red. This is even more expensive. You know, I had to build, if I wanted to switch between these two operators, F1 and F1 prime, I had to build both of them in hardware. So if they're roughly equal complexity, that's double the cost. And then I had to build a multiplexer. And if these output wide data words, you know, maybe 128 bits of data, this multiplexer is also relatively expensive. So this was pretty expensive. It's probably more than double the cost. Well, it's definitely the cost of F1 and F1 prime plus the bucks. So I probably just more than doubled the cost of that operation. So you don't like this as well. You sometimes have to do it. You have to make your operators general enough to do your computation, but there's a cost. Okay, so can anybody think of another way you could do this? There is another technique you could use in an FPGA. So what else could I do instead? And let's say that I don't change this that often. So if I change this every single clock cycle, then probably I have no option. This is what I have to do. Because this I could change every clock cycle because I've got, you know, a control signal there, and I've got these A, B, C going in there. I could change them every clock cycle, that'll be fine. But there are quite a few systems where I only change these once in a while. Again, in communication systems, you often negotiate a protocol by which you'll communicate, and then you use it for a long time. Or filtering applications, once you've decided on what the filter is, you may use that filter for a long time and only update it infrequently if something changes about the channel characteristics in your wireless communication system, for example. So if I'm only gonna infrequently, you know, maybe once every few seconds, maybe once every few milliseconds, let's say once every few seconds, that's easier, change between F1 and F1 prime, is there anything I could do that's more efficient? Yeah, so reconfigure the FPGA. So you could reconfigure the whole FPGA, but if you do that, your system goes down, okay? So it takes maybe 100 milliseconds to reconfigure the whole FPGA, and during that period of time, the FPGA is doing nothing. I mean, its IOs have gone to an invalid state, et cetera. It may actually hang, if the FPGA is connected to other chips, it may actually hang your whole system. And certainly the FPGA for 100 milliseconds is doing nothing. And 100 milliseconds could be a long time. So let's again take the case of a communication system. Basically everybody whose cell phone conversation or internet connection is going through that FPGA just got dropped, right? Because for 100 milliseconds, you reconfigured the FPGA and the system went haywire. So Camillus, and what you may have meant is partial reconfiguration, which is Camillus adjusting. So could we change part of the design while keeping the rest running? And yeah, that's called partial reconfiguration in an FPGA, and the hardware supports it. Okay, so method 2 is to reconfigure part of the FPGA. Okay, because we're going to reconfigure only part of it, we can keep the system operating. We need to carefully think about, you know, what does it do while we're doing this partial reconfiguration, but we can make sure our IOs don't go crazy and so on. Maybe we buffer our inputs so we don't drop anything. So what that does, we've got F1 feeding G1 and F2 feeding G1. So that's what we're doing at first. And what we want to change to at a certain point in time is we want to have F1 prime and F2 feeding G2, okay? So what we need to change is we basically need to change, let me get another color here. So we need to change F1 to F1 primed, and we need to change G1 to G2. And the FPGA hardware lets us do this, right? We can reprogram the whole chip. Partial reconfiguration is basically almost all modern FPGAs support the ability to not just rewrite all of the configuration bits, those 100 million configuration bits, but to rewrite a subset of them. And nowadays you can rewrite in most FPGAs, just one configuration bit at a time. So you could choose any subset of the configuration bits and rewrite them. So we can do this. At the hardware level, we could basically change the lookup tables. We could change the settings of those pass transistors or routing transistors, and we could make this happen. So it's doable, but it's a difficult design flow. So it's done less often than you might think. Except by academics. Academics love it, right? So academics do it probably more than most companies because they're not intimidated by the difficult design flow. Okay, so why is this a difficult design flow? And I'm not saying it's not used, it is used, but you got to be careful how much you use it. And you have to accept that you're signing up for a certain amount of pain. Okay, so why is this difficult? And the dream actually of, again, primarily has been academics, has been to kind of have virtual hardware where you could swap in and out different hardware blocks, much like processors swap in and out memory blocks from disk. So processors have virtual memory. If the piece of memory that you need is not in memory, you just get it from disk, and it happens without you really thinking about it much. If you do too much of it, your programming gets really slow, but if you do a little bit of it, it's fine. So FPGAs actually have hardware where you could swap in different hardware functions just when you need them. So why is this difficult? So any ideas? So you can think of what are the constraints. So the way I'm going to tell you that this is a bit difficult is to go through what are the constraints you have to meet. Okay, so for this to work, you know, what is F1 prime, what conditions does it have to meet? These might be difficult questions, but yeah, so there's compile time for the new function. That's probably okay, but well, it would be a problem if you had no idea what the new function is. But if you as a hardware designer knew I've got the following 2 or 5 or whatever functions, you could pre-compile them all. So you pre-compiled them all. Partial reconfiguration is not going to recompile them. It's just going to load in those bits of bitstream. But yeah, so Marius is right, and so is Rakshith. So the modules have to be similar sizes. Okay, so F1 has been put in a certain spot on the FPGA. F1 prime has to fit in the same space. Okay, so F1 prime must fit in same physical space as F1. Okay, so it means it gets the same amount of logic, RAM, DSP blocks, etc. Now, if it was bigger than F1, you could make that work by just basically saying you're going to make F1 bigger. You're going to give F1 a larger part of the chip. But you have to take the bigger of F1 and F1 prime in every resource and make sure that the spot of the chip that you reserve for them is big enough for both of them. So their area should be pretty compatible. And this also implies, you know, you had to floor plan it. Most FPGA designers like to just let the tools do as much as they can. So they let the place and route engine decide where to put everything. You can't do that if you're going to partially reconfigure between F1 and F1 prime. You have to tell the tools, this is where I want F1 to go. And that's also where I want F1 prime to go. And you need to make sure there's enough of everything in those regions for both. So that's one. Rakshith is also right. You know, interfaces. The interfaces have to be the same. Okay, so the interfaces of F1 and F1 prime must be compatible. Okay, so what does that mean? Well, same signals, right? So you need to, yeah, decide on what would you write in the HDL, for example? What are the input signals of each of them? But more than that, also the physical wires. Okay, so it's not just that there's a certain input that went into F1 and then that same input has to go into F1 prime. That input to F1 has been mapped to certain physical wires. So maybe this is a 128-bit data bus. It's been mapped to certain physical wires that go into F1. F1 prime is going to have to listen to exactly the same physical wires. So it's not enough that it just expects the same data. It's when it's placed and routed, there's a constraint. Where its inputs come in are on certain wires that were chosen by F1, and you got to exactly line up with them. So that's a constraint for the CAD tools and the designer. Designer has to say that the interface, to make sure the interface matches, and then the CAD tools have to match the wires. CAD tools are gradually getting better at this. This is actually a tougher problem for the CAD tools, but they are getting better at it to try to hide some of that detail from the designer. There's another question: what happens to in-flight data? So that's a good question. So let's talk about what happens while you're reconfiguring. So it's going to take a while to reconfigure from F1 to F1 primed. To rewrite all of the configuration memory in an FPGA takes, a big FPGA takes on the order of 100 milliseconds. If you're only going to rewrite 10%, then it'll take about 10% of that, so maybe 10 milliseconds. But 10 milliseconds is still a while, okay? So you need to think about what happens during that 10 milliseconds. So the F1 primed outputs, which are the inputs to G, they're going somewhere else. Must do something reasonable. So a reasonable state might be, for example, if we have valid bits on all of our data, that their valid goes to 0. So G understands there's nothing happening that's useful during this reconfig. Okay, so that's doable, right? You can write hardware that's told the reconfiguration is happening, and the hardware you write in your HDL can basically make your valid signal go low. But you need to think about this. So there's some extra complexity for the designer to decide what should happen during the reconfiguration. We need to drive those signals low. And yeah, I guess this is the last one. So a question from, or point from Edwin about transparency to the user. So, and yeah, so reconfig is fairly slow. Okay, I already mentioned this, about 100 milliseconds times the percent of the chip. So it's 10%, maybe 10 milliseconds. So you need to make sure it doesn't cause an interruption to your system that's going to be annoying to your end user. And in some cases that would be noticeable. You don't want to drop a cell phone conversation. You don't want to drop a whole bunch of network packets. In other cases, it might be okay, but you need to be able to tolerate that. Maddie had a point of latencies may be different. That one's probably okay. So F1 and F1 prime, if they have different latencies, what you tend to do then is it would drive you towards, let's go back up here, a design style that uses FIFOs and valid bits and back pressure. That actually allows you to deal with the fact that if F1 and F1 prime have different latencies, well, you need to make sure that the FIFO is deep enough that it can handle the latencies of both, how long it's going to take to stop F1 and F1 prime. But it doesn't require you to, them to perfectly match, basically. If you used a very inflexible compute model where, you didn't use valid signals and so on, then you're right. You're probably going to have trouble. As you convert from F1 to F1 prime, the odds of everything working out where all your latencies perfectly matched what you expected before are lower. But you can, again, deal with that by using a more flexible compute model that uses valid signals and back pressure and FIFOs to deal with the increased ambiguity. So anyway, so partial reconfig is an interesting, it's an interesting topic. I mean, what I just told you is a bit negative, but the CAD tools are gradually getting better, and it is an interesting capability that FPGAs have that other things don't have. We'll read a paper in a few weeks about Microsoft's data center FPGAs, And they use partial reconfiguration to be able to change what most of the chip does while making sure that the interface to the data center stays alive. So there are certainly uses of partial reconfiguration where, yeah, you want to make sure some basic functionality of the system stays alive. So you don't bring down, for example, 10,000 compute servers because your FPGAs have gone crazy, and you reconfigure all of the compute engines in it. So in those cases, you can think about what should happen and definitely use it. Another place where it has been used some too is the example I was using of communication protocols, where you have a communication protocol that changes once in a while. So this happens in big switching systems. So you have big switching systems that companies like Rogers and Bell buy, where they take a whole pile of high-speed connections coming in from their local network, well, city-scale network traffic, and they're going to basically multiplex them together, increase their data rate, and send them over an optical fiber across the country. Customers change which protocols they want to use, or even which customer changes from time to time. And that doesn't happen that often. So in those big switches, they can make them more efficient if they reconfigure which protocol they're using for which customer. And that can take a little while. For that to take 10 milliseconds is fine. They need to use partial reconfiguration because it's not okay for the whole switch to go down, because if the whole switch goes down, they might lose thousands of internet connections and phone calls and so on. But for the one customer that basically has decided to switch from Bell to Rogers, and we're talking like big corporate class customers, it's okay for it to take 10 milliseconds to reconfigure that piece of the chip and basically put in a different protocol to connect to some other customer. So there are specific cases where partial reconfig is useful, but it is a more challenging design flow. So you need to sign up for the pain and kind of use it somewhat judiciously. Interesting research topic if you want to try to make, how could you make the CAD tools and the architectures more friendly to this? And there is some research in that area. Okay, so let me talk, last topic I was going to talk about today are some streaming optimizations. So we went through kind of increasingly flexible styles of streaming hardware. And again, the basic rule is use the most restrictive one that meets your needs. And you'll usually mix and match them. You'll often wind up with FIFOs and valid signals and back pressure between big modules where you can't quite say who's going to be ready when. And then within that module, you will often not have any back pressure, not have FIFOs, just have general pipeline registers, because once the data arrives that you're just going to compute. There's no stalls that will happen inside. Okay, so let's talk about optimization and streaming, because it is such an important data model for FPGAs. Okay, so first one is pipeline. So we already talked about this. Okay, registers are plentiful. Okay, so they're plentiful in FPGAs, and so pipelining is very effective. It's probably your first go-to place. We already talked about this a bit. Not all pipelining styles are equal. Let me just show you a little pipeline. You can tell me whether you like it or not. Okay, so we've got registers, and I'm showing you something fairly fine-grained. So let's say registers and lookup tables. So I'm looking at register, lookup table, and then that goes out to another lookup table. So this register fans out to two different lookup tables. I'm just labeling them all with a number. So L3 and L4 and L5 all have different functions. They're all physically different lookup tables. Okay, and then finally I registered my outputs. Okay, so and let me put some timing numbers on this. So let's say that this delay from these registers, that registers take 2 nanoseconds, and from this register to this bank of registers takes 6 nanoseconds. So what do you think of my pipelining? Do you like my pipelining? No. Okay, so no one likes it. It's imbalanced. Not great type pipelining. So I could go back to my HDL and I could try to move around my registers, or I could just try to rewrite my HDL. There's a systematic way to do this. It's called retiming. Okay, so it's another optimization that you can do as a designer, and also the CAD tools can actually do automatically for you. So CAD tools have very limited support for automatic pipelining. There are a few cases now where you can tell it it's okay to change the pipelining and they'll try, but mostly pipelining is done by the designer. Retiming is something that, again, a designer can do in a mechanical way, and it's mechanical enough that a CAD tool can actually automate it. So you can also just try turning it on. Okay, so does anybody know what retiming is? Have you ever heard this? You might be able to guess based on the diagram I drew here. So what does retiming do? Yeah, so it moves registers around. So it moves registers across logic. Okay, so let me write that down. So move registers forward and backward across logic. And what it's trying to do is to balance the timing paths. Okay, so we've got an imbalanced pipeline, imbalance here, 2 nanosecond delay there on the left, 6 nanoseconds on the right. We're going to be limited, our clock period is going to be limited to the worst of those two, so 6 nanoseconds, so that seems wasteful. So a retimer is going to, let's see if I can draw this nicely here. Okay, so what a retiming algorithm will do is it can move registers around. So it's going to take this register, and it's going to say, that doesn't look like it's in a very good spot. So it's going to try to move it across the logic. So we'd like to move this register over here. And when we do that, we're actually going to have to create 2 copies of it. Because when we move this register on the other side of these lookup tables, we have to actually we have to basically make sure that the number of cycles we go through on any input to output path has not changed. So in order for that to happen, when we move this register, we have to put 2 copies of it, one here and one here. Okay, so I can do that, and then I could cross this one out. Does that make sense? And let me just draw that out. So, well, let's say I'll just draw that in blue. Try to utilize color well here. So if I did that, I might wind up with a new set of paths where it's where it's 4 nanoseconds from these input registers to these new blue ones, and 4 nanoseconds from them to the output. So now I can clock this at 250 megahertz instead of at about 166 megahertz. Okay, so the nice thing about retiming is that this can be done automatically. Okay, or you can do it by hand. So you can also do it by changing your RTL by realizing this is an option. And the CAD tools don't do this perfectly, so it is still a good idea to, if you've created very imbalanced pipeline stages, to actually change your RTL to try to balance them some. The CAD tools are pretty good at doing the fine-grained balancing, but if pipeline stages are very imbalanced, they have a lot of work to do and they can get confused. They probably won't do as good a job as if you give them a better starting point. The reason this can be done by hand is it does not change, it doesn't change anything observable outside of the chip or the module. Okay, so it does not change the circuit behavior observed at the IOs. And that's why a CAD tool can do it automatically. A CAD tool can't do pipelining automatically because it changes at least the latency observed at the IOs and that can break your system. So if you have certain latency constraints, it's wrong. Also, a lot of, usually your control logic may depend on certain latency and so on as well. So unless you're using a style that is like latency insensitive design, which I described briefly earlier, that paper by Carloni, then changing the amount of pipelining requires changes to your control logic, and a CAD tool just can't do it. So, and no matter what, it's going to change the observed number of cycles it takes for things to come out of your design. So generally, CAD tools will not automatically pipeline. There are a few options now where you can tell it on certain signals. I'm telling you this is safe, you can do it. But they're more unusual because in general, it is dangerous for a tool to try to pipeline. It's going to generally break your design. And so you need to find a tool that supports it when you give it detailed constraints saying, I'm telling you it's okay here. But retiming, as I said, because it's not observable outside, can be done automatically. Now, many CAD tools still don't do retiming automatically. You'll have to turn it on. So by default, they won't turn it on. Any idea why? This is gradually changing as FPGAs kind of do more and more advanced optimizations to registers. They're starting to turn on retiming by default. But for many years, after the FPGA CAD tools supported retiming, it was always off by default, and you had to go turn it on if you wanted it. So any idea why they don't just turn this on by default and just everybody gets it? Like, why would you have options to ever turn this off? So compile time. So it's true. It's a complicated optimization, so it can increase your compile time. So if you don't need it, that's a good reason not to do it. Retiming, it's hard to tell how your stuff affects your circuit timing. So I guess you're saying that you'd be difficult to tell if you're writing your RTL in a way that was more or less timing friendly. That could be true, although if retiming always made it better, then probably the CAD tool vendors would be happy with that. They just say, you don't have to worry about it anymore. So I guess that one's a plus minus. If basically you could write arbitrarily unbalanced RTL and the retimer just made it all the same speed, the CAD tool vendors would probably consider that a win. Maybe its performance wasn't very good, its applicability was limited. True, initially it wasn't that good. It's gradually getting better, and I guess we'll talk about this later in the course. FPGAs are also getting more and more register rich, including even putting registers in the interconnect. So it's getting more important as they do that. And a key one is harder to debug. So it also can increase area usage too. So it's also true. The example I showed you here, we retimed this register, but we made 2 copies. So there was some increase in area usage. By the way, the opposite could happen. You can have 2 registers. If I'd originally put these 2 registers here, in these blue spots, let's see, we'll highlight them. So if these were my original registers, and it turned out that that this was, all of these connections were really fast and these connections were slow, the retimer could actually move these 2 registers backwards, over this way, and they would actually turn it back into 1 register. But usually it does increase register usage. It's more common that it gets moved from one spot to multiple and it increases register usage. But the key reason they don't turn it on by default was harder to debug. So if you actually bring up a retimed circuit in a simulator, you don't know what the registers are. So in your HDL, you wrote, this is an enable register, and this register represents this state, and this register is the sum of the following 3 values, and so on. You gave your registers hopefully very good names, and you understand what they do. After they've been retimed, they've been moved around, you don't actually know what those registers are doing exactly. They're hard to give names or describe their functionality. They're correct, but if your design is not working and you bring it up in a simulator to try to figure out what's going on, you have a bunch of registers where you go, I don't know what's going on here. So because of that, that's one reason you turn retiming off, right? When you're trying to use debugging tools in the FPGA and examine the register state and see if it matches what you expect, retiming makes that considerably harder to figure out what's going on. So you typically want to go and turn it on, not when you're debugging. Basically, when you're pretty sure your design works at a logical level, and at that point, then you can retime and get some extra speed. So, okay. So that was one optimization. So retiming, well, two, I guess, pipelining and then retiming. A third one. Now let me start with the motivation for this third optimization. So some IP blocks can be actually faster than you need. Okay. So let's say that you're grabbing a module that somebody else wrote. So say it's faster than one stream. So you've actually got a module that's faster than you need, but you've got a lot of processing to do on different streams of data. So you can make use of that extra speed. And the way you make use of it is another optimization called time domain multiplexing. Okay, so we can time domain multiplex across multiple streams. Okay, and when we do this, the best way to do this is actually to use the same technique we used with valid bits. So with valid bits, instead of trying to make some complicated finite state machine to say when our data is valid, we just tagged with the data is valid. Okay, so we know it's valid because we checked the valid bit. So in a similar way, we can tag our data with a stream ID. Okay, so what do I mean by this? Again, I think it's best to show an example of this. So let's say I've got a function A, and I've got a function B, and both of those are going to go into some Fifo. And I've got some function H that another person on my team wrote or I bought from another company. It's expensive, it takes a lot of space, but it's really fast. So let's say that's an expensive, pretty big operation. Takes a big chunk of the FPGA. And let's say it runs very fast though. It's been very well pipelined and designed, runs at 400 megahertz, whereas these other operators are not as fast. Say they run at 200 megahertz. So basically, I can make two copies of F, so FA and FB. Each of them is going to process a different stream of data. So maybe data coming in from a different antenna on a cellular base station. Those two streams get interleaved in this Fifo and sent at a higher speed through H, this really fast IP core that I bought. And then afterwards, we're going to take them apart and put them back into two Fifos to go to the rest, either go out to the outside world or go to the rest of the processing. Okay, so what we've done is we're basically just using one copy of H instead of two. We got two streams, A and B, that we want to process, but H is so fast that it could actually process both of them if we could just put A and B together in time. So we're going to time domain multiplex H, basically send it data from different streams every second cycle. So we only need one copy of it instead of two. And again, it only makes sense if you have a high performance H where it can keep up with that. And if you do this with finite state machines and so on, it's going to be a mess. So it's again best to do it by tagging your data. You have data and you used to have valid, now you've got data, valid, and stream ID, so that the data can be taken apart when it comes out of H and put back into the proper Fifo. And I think the last optimization I'm going to talk about is, so hopefully that's reasonably clear, the concept. One of the special cases where time domain multiplexing can be really useful, so I just gave you the example of I've got a fast IP core that I bought. I'm trying to get as much out of it as I can. Another case that's useful is loops. So we talked about loops, and loops are annoying because we can't pipeline them. We can try to go rewrite the loop and change its latency, but we can't just pipeline it by putting more registers in. We actually have to go redesign the logic. And sometimes we just can't figure out how to do that. You've got a loop and you can't figure out how to get rid of it, or how to make it shorter, or how to get more registers in it. So what you can do then, you can't pipeline it in a normal way, but you can time domain multiplex it. So let's see, this is always this thing of what the best way to explain this is. I'm going to draw you an example. Well, let's see. So basically, let's draw the same example I had before. So I've got F1, It's feeding an F2, which goes into a register, and that produces a Y value, Y of I, and I've got an annoying loop, right? So there's a loop where Y of I goes back, and I have an X value out here. Okay, so I've got X of I going into this. And we saw earlier we can't pipeline now, so that's annoying. What we can do is we can interleave two streams of data. Okay, so I'm now going to say I've got an X1 stream of data and I got a separate independent X2 stream of data. So again, signal processing is a good example for this. Maybe these are two different antennas on a cell phone base station. So there's no interaction between those two different antennas. If I have two streams like this and I flip back and forth between them every single cycle, then I'm basically time domain multiplexing this circuit. And what that allows me to do is I can now put a pipeline register in here. Let me change my color. So that pipeline register, if I only had one stream of data, I just broke my hardware because I changed my computation because I don't have a complete Y computed. But with this change, it now works. Basically what happens is I'm computing two output streams. Okay, so I'll compute, let's see if we draw this in a bit better way. What I'll compute is now Y1 of 0, so the first Y value. And then I'm going to compute Y2 of 0. Okay, so again, I got two streams of data coming in, X1 and X2. Every second cycle, every cycle I flip between them. Okay, so cycle 1, I send in X1, the first sample. Cycle 2, I send in X2, the first sample. Cycle 3, I go back to X1, but send in the second sample, and so on. So now I'm going to output two different streams of Y values. And there's streams. So I get a bunch of different values in time, and so on. Okay, so time is going that way. And if I go and analyze what I'm calculating, it's actually correct. Okay, so if I take Y1 of I is equal to F2, right? So I've got this block F2, and it's F2 of some function F1. I've got this block F1, and it's a function X1 of I, and it's a function of the Y value that I had 2 cycles ago, because I put this register in here. Well, the Y value I had 2 cycles ago is actually from stream 1, and its value I minus 1. Okay, which is what the original hardware would have done before I did this time domain multiplexing and put in this pipeline register. Okay, and I also am computing another output stream, Y2 of I, and it's exactly the same, right? It's a function F2 of a function F1, but it's of the other half of the X's, the stream X2, and again, it's of Y2. It's of the Y value that happened 2 cycles ago, but the Y value 2 cycles ago is actually Y2, the second stream, and 1 entry back. So hopefully that's clear. This is a spot where I usually confuse people. Does this make sense? So yeah, by interleaving 2 data streams, I now can increase the latency of this loop by 1. So I can double it from 1 cycle to 2 cycles, and everything is correct because of the fact that I interleaved 2 data streams. In fact, when I interleaved 2 data streams, in this loop, I had to increase the latency of the loop to 2, otherwise it wouldn't work. But doing those 2 things together, they essentially cancel each other out. I wind up computing 2 different streams of data, and they're both correct. So this is only useful if I actually have 2 different independent streams of data. If I didn't have that, this optimization is kind of useless. You know, if I have no X2, then I'm just putting blank data in every second cycle, which is not really useful. But if I have another stream of data that I can process, then this is an efficient transformation, because what I've done is I've said the same hardware can process 2 streams of data, and because I've got twice as much registering in it, it's more deeply pipelined, it probably clocks at twice the rate. So this can actually process each stream at around the frequency that it used to process them at, but I can now do 2. So I've made my hardware more efficient. Does that make sense? I'm going to take silence on chat as yes. So, Andrew, I'm going to ask you, did it make sense to you? Because I lost you, I'm in trouble.
Yeah, it did.
Okay, it's good. Thank you. All right, this leads to another, yeah, I guess, so in this case, you have to do pipeline, otherwise Y1 will use the previous value of Y2. Yes. So in this particular case where I've got a loop like this, and I'm going to interleave 2 streams, I have to do the pipelining at the same time, because the interleaving 2 streams in a loop like this is actually going to break my behavior. The doubling the latency around the loop corrects that. So the 2 optimizations, the 2 changes together cancel out. But if I did one or the other alone, it would not be correct. So I have to do them together. So that's a good question. So this leads to one more mechanical change. So basically optimizations that you can apply in a fairly mechanical way are very valuable because they're just in your toolbox and you can just do them. So this is another optimization called C-slow retiming. All right, so the retiming is a hint. This is going to use retiming. Okay, so what does C-slow retiming do? So the first thing it does is it makes C copies. Okay, so C is some parameter, the number of times you're going to slow down the circuit or how many streams you're interleaving. So in the example I just gave you, C was 2. I took 2 streams and I interleaved them. So if I want to take C streams and interleave them, what I do is I make C copies of each register. Okay, so in the hardware module that I want to do this for, every single register turns into C registers, and they look like this. So if C equals 3, I would just have 3 registers in a row. Then you add time domain multiplexing circuitry, which is basically what I have up here. So a mux that's going to flip back and forth cycle by cycle between different streams. And I'm going to send in C interleaved input streams. Right, so interleave means, you know, cycle 1, I send in stream 1, cycle 2, stream 2, cycle 3, stream 3, and then cycle 4 back to stream 1, if I was doing C equals 3. All right, and then what I do is I retime to distribute registers. Okay, so what that would have done on this circuit is C-slow retiming. Maybe I'll just redraw it so it's basically not so messy. Okay, so I've got an F1, I've got an F2, and I've got, used to have 1 register, but with C-slow retiming, let's say I'm going to retime by a factor of 3. I'd actually convert that to 3 registers. And that output of that goes back here. That's what I had before. And this is my Y. I also need to time domain multiplex my inputs. So I'm going to take 3 streams now, X1, X2, and X3, and time domain multiplex my inputs. So I've done the first 2 steps, and this isn't going to clock any faster, right? My critical path so far doesn't look any better because it's going to be from the output of this register all the way back through these 2 operators to the input of this register, which is not really going to be any better than it was before. But now what I can do is I can invoke my retiming algorithm, which again, CAD tools can automatically do. And I'm going to move, the CAD tool is going to basically move these registers around. So it would probably move, you know, this register would probably wind up moving to there, and this register would wind up moving to there. And I would get, hopefully, you know, ideally 3 times the performance. In practice, I probably won't get quite that much, but maybe I'll get 2.5 times the performance because my critical path is much shorter. My registers are now nicely balanced. Okay, so what's the gain of this? If I had a fair amount of logic in loops, then by doing this, I've increased the latency around a loop. I've increased the number of registers that I can put in the loop. I've retimed them to cut up a long critical path into smaller pieces. So if all goes well, you could clock approximately C times faster. Which means that each of your streams actually doesn't slow down if that happens, but you get, C streams of data. Okay, and you get them through the same hardware. Plus some registers. So it did cost you some extra registers, and it did cost you a little bit of time to make multiplexing circuitry, so it cost you a little bit. And if we actually got an increase in our clock speed of C, so in this case 3 times, you would actually get each of those streams coming out at the same rate. Now in practice, I'm unlikely, if I did C slow retiming with C equals 3, I'm probably not going to get 3 times the clock frequency. So, in this case, maybe I get 2.5. Each stream slows down some, but I get more streams through, so my throughput goes up. So if I'm in a system where I've got lots of work to do, again, I keep coming back to wireless. I got lots of antennas going on my cell phone base station. Then this could be a good optimization. I get more throughput through the same hardware because I've got lots of registers and lots of independent work to do, and I get rid of this limitation on how deeply I can pipeline because of the fact that I have loops. Somebody has a good question. What determines the upper bound for C? So the upper bound for C, I guess, is 2 things. It's how many streams of data you have. So if you only have 2 streams of data, then going beyond 2 streams is not useful. But often you have a lot of streams of data in some of these systems. The other limitation is, I told you if I did C slow retiming on this with C equals 3, maybe I get 2.5 times the clock frequency. As you start making C very big, your clock frequency will start to saturate. So if I did C equals 100, unless I'm a really bad RTL designer, I probably don't have 100 lookup tables in series on some pipeline or some loop path. So I probably can't make very good use of all the registers. And that would be like an extreme example. Once you've basically got nothing but one lookup table or one multiplier in between your registers, adding more registers, has diminishing returns. You might be able to get rid of some wiring delay, but after a while, there's just all your delays are just the remaining logic that you can't put registers in between. So that could be a single lookup table, it could be a single multiplier or a single RAM block, but you're basically limited by things where you can't get a register in the middle anymore because you're down to kind of indivisible units. And going beyond that's not useful. What that point is depends on how complicated your logic was in this loop. If your logic was pretty simple and you had 2 or 3 lookup tables, then probably going beyond 2 or 3 in C slow retiming is not useful. If your logic was very complicated, then going to higher values of C could still get you something. But usually this is going to be like, not enormous numbers of C, like values from like 2 to 4. If you have really big loops, maybe 8 are probably reasonable. And beyond that, the odds of getting any improvement are very limited. And FPGAs are register rich, but they're not register infinite. So if you go completely crazy with registers, they will eventually start limiting you'll run out, right? So they'll start limiting the size of design you can fit in the chip. Anyway, that was a long answer to your question. Hopefully that answered it and was not annoyingly long. So, okay, so that is all I was going to talk about for this week. If there are any other questions, let me know. For next week, basically, streaming is so important. We talked a bunch about all sorts of different models of streaming and optimizations for it. Some of which are just general hardware optimizations you can use. We'll talk about other compute models next week as well, which are generally not as efficient for high throughput as streaming, but can be useful in other situations, like where you have more complicated control or you don't need as much throughput and you want to get more area reduction. So we'll talk about a bunch of other more diverse programming models next week. and add them into your toolbox. And as I said, we'll release assignment 1 shortly, which is about doing a FPGA design, optimizing it using techniques like pipelining deeply, and comparing some of the different programming models that we're going over here. Okay, so with that, feel free to sign off. I'm going to stay on the line in case anybody has a question. I haven't forgotten that I promised to do kind of a coffee time. I'm just kind of waiting for assignment 1 to be released and for me to work through a few things before I start doing the first coffee time. But my plan is to do a couple of different times so that they're friendly to different time zones. And I'll post those on Piazza. Okay, so thanks everybody. As I said, I'll be here. I'm just going to stop recording now.